Welcome. So this next chapter is on current and resistance. And you could argue and say this could be a very simple chapter because I can just tell you about current and tell you about resistance. But there are other terms you'll hear coming up that you need to know about. But in the end, it is just current and it is just resistance. Okay. So let's visualize something. So here we have the cross section of a piece of, if you like, a piece of wire. And we have charged particles passing through it. We think of current as being positive flowing particles. We know that it's the electrons that flow, but it was decided before we knew that, so we kind of stick with it. Current is the rate at which charge flows through a surface of area A. So basically, the average current is, my current is defined as being the change of the amount of charge over the amount of time. So you can count how many coulombs are going through, and if you have 5 coulombs in 10 seconds, that's 0.5, whatever, we'll call them amps. If you count 0.7 coulombs in 1 second, it's 0.7 amps. So it's just that. Current is measured in amps, named after ampere, and so an amp is a coulomb a second. The direction of current flow is taken to be the direction of flow of positive charges, and we know that that's not what the loose bit in a piece of wire is the electrons, but we just decide to take it the other way. Sometimes we will talk about positive charges flowing, sometimes to visualize we'll talk about negative charges flowing, but when we're talking about the current, we are imagining positive charges flowing. So current flows in an external circuit outside a battery. Current flows from the positive to the negative. And that's the way we do it. Well, you know, we finished Physics 1 and we've got all these tools in our toolbox and we want to play with them. So we start asking ourselves questions and we say, well, all right, I get this idea about positive charges flowing. I wonder how fast those charges flow. And what we realize is it's not quite as easy as it may seem. I want you to look at that bottom diagram. And I want to use an analogy with gravity. So here's my boulder, and the electric field is pointing upwards. So here's my negative charge. Here's my electron. Oh man, it's not going to work so well. Anyway, here's my boulder. It's going to go, and it hits these pins. These pins are all over the place. These pins are like, you know, a little forest of pins. And what happens is well, I might as well tell you the real thing I'm visualizing. When I was a kid, I'd save up a little bit of money to go on vacation, and then I'd find an arcade. And the first thing I'd do is I'd go to that arcade and I'd spend all my money in the arcade. And crazy games. And this one machine, it had a little slot where you put your money in, and then your money would literally appear. Not even a ball. Your money would appear. And it would bounce backwards and forwards and backwards and forwards and backwards and forwards. And here, there'd be a whole bunch of trays. And one of them had a hole in. And it was usually like this guy here had a hole in. And if your coin went in that hole, you won by getting your coin back. There was no jackpot. There was no nothing. You got your coin back. So winning was breaking even. And I'd play it. I loved that game. Because it would go ding, 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 ding. Not even bells. It would just, I could hear it hitting the nails going ding, 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 ding. And I'd lose. And I'd get my next coin and I'd put it in and get my next coin and put it in. My brother would stand there going crazy because he knew that I would be out of money by the end of the, 20 minutes. And I'd spend the rest of the week asking for money from him and my parents. And he was, quite the opposite. He saved his money. And he'd look at something and go, that's worth 1 coin, and he'd do it, and then he'd never play it again, you know. All week he had money. He seemed to have more money as the week went on. And he ended up owning his own business and driving a nice car and all that kind of stuff. And I've always got enough money to go, but I don't ask people for money anymore. I stopped that. But it's funny how personality, and that I believe that's not learned. That's just, it's personality. I think that having 2 siblings means that it gets exacerbated. I think he's more penny wise because of me, because he saw the way I behaved. And I just couldn't stand it. So I actually went worse. I would like, oh yeah, watch this. I'm going to go through all my money. So it separated us. I think siblings tend to do that. But what's going on? Gravity's trying to pull it down, and this thing keeps hitting these little mass centers, and what they do is they interact and bounce off, and you see little parabolas in between. This is like projectile motion, backwards and forwards. And there's the actual velocity of the particle, which is different from the rate of progress of the particle going down through the machine. It's actually traveling quite fast along its path. But because it keeps hitting these things, its actual progress is quite slow. So we've got to distinguish between the so-called drift velocity and the actual velocity, the actual speed of the thing. They're not the same. If you are running very quickly through a crowd, you'll keep hitting people, so your progress is quite slow, but you are running very quickly. So we've got to name those 2 things differently. And we call your progress through the crowd your drift velocity. You're not really drifting, but it's your drift velocity. And we can call how fast you're running your velocity, your speed, your whatever. We've got to distinguish between these 2. And then the second thing we've got to do is got to set up some nomenclature. So we're imagining a little tube of wire, and it's got a distance delta x, and it's got an area A, and we're going to imagine a charge q, and we got a drift velocity. On average, this particle, it's bouncing into a whole bunch of things. Who cares? We're taking its progress velocity. We're taking the drift velocity, because it makes math easier. Well, how many particles do we have? Let n be the number of mobile charge carriers per unit volume. Copper has a different number from aluminum. I was stunned when I came to the States and I found that they would wire houses using aluminum. I don't think that's done in Britain. I think it's always in copper.
It's not done anymore.
Oh, it's not done anymore? Okay, yeah, it's like...
It's popular in the 70s.
Okay, yeah. So, different materials have different numbers of free charge carriers per unit volume. Let delta Q be the charge in the section being considered. So how many charges do we have in here? Let's call it delta Q. Let Q be the charge on each little charge carrier. So that's got a Q on it, and that's got Q on it. And we say, well, my total charge must equal the number of charge carriers I have in my box, in my tube, times the charge on a charge carrier. So this is the number of charge carriers in my little piece of wire. And where does that come from? It's the number of charge carriers per unit volume times the volume. That's where that comes from. Yep. And then we say, well, let Vd be the drift velocity of the charge carriers. So my total charge in my little piece of area is the number of charge carriers. And then what I can say is, well, I can work out that delta x by using my drift velocity times the time. Isn't it? If I'm traveling at 5 meters per second for 5 seconds, I've traveled 25 meters. So I did that. And then what I say is, well, all right, my current is my charge per time. Let's divide this thing by time. Oh, look, that delta t cancels. So I have I is equal to NQ V drift times A. So my drift velocity is equal to I over NQA. And that's another equation that I don't expect you to know. But let's look at it for a minute. If I double my current, I get twice the drift velocity. Everything else staying the same. How can I get double my current? Get things going through twice as fast. How can I get? How can I double my current? Have more charge carriers. Double your number n. How can I get a bigger current? If I could increase the charge on a charge carrier, and I can't do that because they're electrons. That's the way it goes. Or I could increase my area. Got to be a little bit careful with that last one, because electrons like to stay on the outside. Certainly AC, there's this thing called skin effect, where you don't have much current going through the middle of a piece of wire in AC. It's mainly going through the outside. So maybe the area is not the area that you think, but you know, we'll just... That's actually an interesting point in itself. I've just opened a can of worms there, because the free charge carriers are originally embedded throughout the material, so maybe it's still okay. Okay, so that's interesting, but you don't need to know it. You know, you don't need to remember it for the test. You know there is a thing called drift velocity, etc. I'd like to know the current density, and the current density is my current, and here I've got to be careful with my signs and make them really distinct, divided by the area. There's my current. How much current do you have flowing through this piece of wire divided by the area? And if I remember that my current is equal to NQ, the drift velocity, times my area, then my current density equals MQ times the drift velocity. Okay. Call it J. You'll very rarely come across J unless you do some specialized stuff, but it's there. Okay. We're going to use it later, like now. For ohmic materials, wires, that kind of things. For ohmic materials, the current density is equal to that which is your conductivity. Sigma is conductivity times the electric field. I think that's defined as that. My electric field is my delta V over delta X, which in this case is L. And now I've got to be careful about my symbols, because that looks an awful lot like an I. And my J is equal to my I over my A. So my delta V is equal to my J over sigma, which is J over sigma, which is my E, and my E times my L, so that's an L. Yeah, delta V equal delta V. Did I do that right? Did I do that right? Delta V equals EL. Let's have a look. That's my delta V. And I substitute in for my E. I'm making hard work of this, I know, I'm sorry. Let's have a look. So my E equals, so delta V equals EL. And my E, my E is equal to J over sigma. So put those guys together, I get delta V is equal to my J over sigma times my L, which is what I've got there. And the next little bit is my J is equal to I over A. So I have delta V is equal to I over A sigma times L. So I get, that is I, and that's an L. Yeah. Cool. Just the I's and the L's get confused in that an awful lot. And I don't particularly care about that. So we can define a resistance, and the resistance is equal to my my resistance is equal to sigma A over I. Sorry. My resistance is equal to sigma A over L. So I define that as R. So I end up with R is equal to delta V over I. Or, Ohm's law, you got to know this. This is just going to keep coming up, coming up, coming up. If I plot a graph of current versus voltage, the slope does not equal resistance. I should plot a graph of voltage versus current, and then my slope would be resistance. But typically, because I control V and I is what I get, I put my independent variable on the x-axis. So I put my V on the x-axis. And so I say I is equal to 1 over R times delta V. And so the slope is 1 over R. So watch out for that. It's a little quirk. It's like you don't think about it and then it's backwards. Okay? It's just the way we tend to plot the independent variable horizontally, and most often the independent variable is the voltage that you apply, not the current that passes. Just by the by, so I was doing this equation for the first time, and my dad heard me talking about Ohm's law, and he goes, "Which one?" And I said, "What do you mean, which one?" He goes, "There's 3 Ohm's laws." And I said, "No, there's only one." He goes, "No, there's 3 Ohm's laws." I learned about it. So my dad did I tell you about that? He wanted to be a pilot during the Second World War. He failed out of flight school because he couldn't do the depth perception very well. So he said to the sergeant said, "I'm sorry, son, but you've failed." And my dad said, "What does that mean, Sergeant?" And he says, "What happens now, Sergeant?" And he goes, "Well, son, in about a week's time, we're going to have a test. And the people who pass the test sufficiently will go to navigation school, because we need navigators as well as pilots." So that was 18 months of schooling. And those that don't pass will be sent to gunnery school. Gunnery school was an afternoon with a gun. At that time during the Second World War, the life expectancy for a rear gunner was 4 hours in the air. So my dad was looking at, if I pass this test, I get 18 months in navigation school. If I fail this test, I get an afternoon shooting, and then I do the next opening. And the next opening is always the rear gunner, because that was the weakness in the plane. So yeah, basically what? Maybe you'd get 3 trips out of it. You'd have maybe 3 days. And then the chances are, unless you were lucky, that, he said, the pressure, don't talk to me about pressure, he goes, it's incredible pressure. So and for him it changed his life. He went from being a gay guy, he left school at 14, and because of that experience he learned math and he learned some electronics and, he learned some education. And so that set him up for the rest of his life. And if he'd not done that, he was a butcher's boy. He was chopping up meat and stuff like that. So big difference. So he learned his three Ohm's laws, and the first Ohm's law, he quoted them to me. He goes, "V is equal to IR. Number 1," he goes. "Number 2, I is equal to V over R. And number 3 is R is equal to delta V over I." 3 equations, 3 laws, he goes. And me and my brother are like rolling about the floor laughing. And we're going, it's the same law. And I thought about it afterwards. And he was like, yeah. And you think about it, and you want people to learn this stuff, and you don't know what their math's like. They've not done algebra. You just teach them 3 laws, and they learn them, because they need to learn them, or else they're going to go to gunnery school, So they learn them, and, it's, in a way, it's really clever. And I must confess, is anybody in the military? Anybody? So I've been very impressed. When I've met people from the military, by and large, the military seems to do a good job of teaching anybody to do any job by breaking it down. Is that, have I just been like fortunate in who I've seen? But they just seem to say, like one guy was a mechanic on aeroplanes. And basically he learned how to do that. And then he gets a promotion and they send him to dental school. And he's learning to be a dental hygienist because then he's going to be in charge of this group of people who are going to be doing dentistry for the next 5 years. And I said, but you have no background in that. And he goes, they break every job down so that, you know, you learn it and you can do it. So is that your experience, or is that just I've met people who are...
Well, it's not that the training is good, it's that you don't have a lot of options.
Oh, okay, yes.
So you know, in my experience, I was a medic,
Yeah,
and I don't like medicine.
yeah,
And I hate it. But it was either that or I was going to be a NP.
oh man, okay, yeah.
They stand guard all the time.
Yeah.
I wasn't going to do that, so I had to learn it.
You had to learn it.
Does that, does that
Yeah.
make sense?
Yeah.
It's not that the school, the training's not that great.
Okay,
But,
okay. But you were motivated really well. Maybe we should do that. Maybe we should do that. If you don't pass this test, I'm going to make you stand outside my office for 4 days. Anyway. So this is bedrock. This is very important. So all right. So we have resistance. Resistance is like weight. Materials have resistivity. That sample has weight, but that material has density, yeah? That material has resistance. So that sample has resistance, but that material has resistivity. So we can say resistance is like weight, and resistivity is like density, actually. No, density, yeah, density. Maybe that's why they have the same symbol. So the material property is resistivity. The sample of that material then has a resistance. Okay? We want to build some materials. The resistivity of the material is 1 over the conductance. The unit of resistivity is the ohm meter. For a uniform sample, cylindrical sample, we can say the resistance equals rho L over A. That's an important equation. It's the resistivity times the length over the area. If we have ohm meters multiplied by meters and divided by meters squared, we get ohms. So that's a really important equation. So V equals IR, and that very, very important. What is the resistance of a cylindrical resistor that is made of? Let me just have a quick look. Let's stop there. We got like a minute before the end of class. Let's just stop there. And